Find the answers to questions you may or may not have asked yourself here at Science, Conversations on Cognitive Science, hosted by Elisa Palmer and Sönke Löw. Whenever we are walking, moving, or do any task, our brain is involved to a certain degree. Like, especially for movements, our motor cortex is involved and not only monitors, but also controls how well or unwell we are able to perform a task or movement. And today we are going to talk about, research that looks exactly at that, areas of the brain that are involved. And we'll talk to Mo Nipshagen, who is currently doing their research in that field. So welcome on our podcast today.
Thank you.
And as always, we like to play our short little welcome game, and I will start sentences, and I want you to spontaneously continue them. And the first sentence is, as a kid, I always wanted to be.
I think a carpenter was where I started out at, because that was what my dad and my bigger brother were. And so I was just always very intrigued by that pursuit. I was like, oh yeah, of course, that was what I'm going to do. I've veered very far from that path by now.
The next sentence is, if I was an emoji, I would be.
Just in terms of use, probably the laugh sweat smiley.
The nervously laughing?
Yeah.
I'm also that one.
I'm nervous a lot, but I laugh a lot as well.
My favorite thing to do on the day off is?
So many things if I take day off. I think spending time with friends, if I have the energy for that, or otherwise just hunker down and do whatever I want to do at home and just have my own little sphere without other responsibilities from outside crashing in.
That sounds amazing.
Right now, I'm most fascinated by?
Ooh. I have to choose one thing. That's a difficult question to spontaneously complete. I'm most fascinated by... No. I think in leading up to the what we're going to talk about as well, I think currently I'm very fascinated by the kind of baseline assumptions we're making about how the brain works and how the mapping of movement works. There's been some really interesting research that kind of calls some of that baseline assumption into question, and then question those questionings. That's something I've been sidetracked on for a few weeks ago. And I think generally how we do the research is something I'm currently super fascinated in, just like on a more basic level, a bit removed from what I'm my research is generally more applied in that level, and thinking about how do we even approach these things has been something that has been on my mind a fair amount.
The last sentence is, I know it's time to call it a day when?
I just start staring through my screen, and the words that are coming from my keyboard don't make sense anymore.
Is that usually a specific time of day, or are you working at all times and just happens after you've worked for too long without having a break?
I think it's just after working too long. I'm trying to get a more structured working hours in, but currently it's more at the end of the day after having done a lot of work, and that can be anywhere between 3 in the afternoon if I started very early, or 9 in the evening, in the night.
Oh.
We have heard that you are still in the field of doing research yourself, and that's why we invited you to the podcast. But can you maybe shortly explain what your position is right now and how you got there?
Shortly, as in what I'm doing right now, as in my PhD position, or how long do you want this to be?
Rather short, I guess.
Yeah,
but
okay.
A bit your scientific journey and the position you fill in. And
okay, but my scientific journey, as in where I started when I first stepped into a campus and how I got to now, but in 3 sentences or something.
Yeah.
Okay.
That would be nice.
I started studying physics actually in Kassel and dropped out because it turned out to be too far removed from anything in particular. And then I picked up cognitive science in Osnabrück. And I really enjoyed that, and because I wanted to work on that interface between humans and technology, and how can humans and technology work together. And particularly was intrigued by, well, brain implants and like brain-computer interfaces, which we're going to talk about more, which then led me to go to Nijmegen in the Netherlands, where I started a master's for cognitive neuroscience and neurotechnology at the Donders Institute. And this is also where I continue my PhD now, in a kind of inter-institutional collaboration. Like I'm working with Maastricht, the Uniklinik Maastricht and Utrecht and Nijmegen. So I'm working like in this trifecta a bit. Was that short enough?
Yeah, that was perfect.
That's great. I was honestly just, while you were talking, thinking about, now I'm a bit more afraid to pronounce Dutch city names, because
I don't speak Dutch much at all. It's enough to like get a very short and simple interactions across, but I try my best to not butcher the names too much. Yeah. If any Dutch people are listening, I'm sorry, but I try my best. It's fine.
So you've mentioned that, well, you don't really have a ordered schedule, but how would your normal day in your research look like right now? So how do you start? What are you doing? Are you doing research on the brain? Are you working with data? How can we imagine your usual day?
Yeah, so my day-to-day work is at the computer. Most of my work, like I'm at the artificial intelligence department, so most of my work is using data and data analysis and building models and reading papers. I don't directly work with like human participants. I don't directly work like in the clinic, etc. That's what my collaborators do, and I then work with the data they produce more so. So my day-to-day is getting to the office, seeing what I have to do, and then sitting at my computer, standing at my computer all day. And then that's reading papers, trying to catch up with what's going on, like finding what I want to do next, or what I'm currently doing, or coding and trying to get my models to run, and then hopefully see the success and take it from there.
And what's the kind of main field you're following when you're reading papers or coding?
I think it broadly falls under computational neuroscience. Like most of my work is computational in nature, so it's about like modeling, but it's also the ethics or like approaches to doing implant research in the first place. It's also about like more large scale, like how do we map the brain, or like how do we interact with the brain, and then every so often things that spark my curiosity, of course, that are not directly related to my work, but that I'm interested in, and whether that is like just slightly tangential, which is like reconstructing something else that isn't motor movement, but using some like other methods, or like speech, for example, or like further outside. Like I still have a broad interest in like cognitive sciences generally.
And on a high-level idea, your research, I mean, you said that you are only participating in like one step of some pipeline, but can you maybe say to us what the input is and what the output should be from that pipeline?
Yeah, like the overall, like I think it's described as like a big machinery, and I'm a small cog or something in it, like, right, like just try to make it spin. Overall, the idea is to build a brain-computer interface that is able to help locked-in patients or like severely paralyzed patients. In the people I work with, that is particularly targeting ALS, so amyotrophic lateral sclerosis, and then like the very late stages of that. But like very similar work is done on like tetraplegic people. So that's kind of like the people we're targeting with for our work. That is like the interest group for what we're trying to make. And the BCIs are supposed to enable some amount of autonomy or communication or general interaction with the environment again. Like if you're severely paralyzed, or particularly late stages of ALS, your brain still gives a signal to move, but your body isn't able to follow anymore, right? Is that because your spine is broken, or your nerves or muscles have degenerated? But the signal of the brain still works. The output just doesn't work anymore. And the BCIs that I'm part of researching are then trying to make a new output channel basically to interact either with communicative devices like tablets or like spellers to make words and like communicate that way. And I'm interested in mapping like motor movement into continuous signals that can be then used, like a mouse pointer on a screen is such a continuous signal, for example, so you can like navigate around and move things again.
Do you use brain data to know what people might want to do, or do you use eye tracking? What kind of data do you use?
So I exclusively work with invasive brain data, so with electrocardiography, ECOG, and stereoelectrode data, so like a depth electrodes, so like long shafts that are inserted in the brain.
So it's not like a cap on the scalp, but the patients actually had an surgery where their scalp was opened and they had some kinds of electrodes implanted into their brain. Okay.
So most of our data that we work, like our research data, doesn't come from actual locked-in users, but from epilepsy, people that are in for epilepsy treatment. Because when epilepsy is pharmacoresistant and like the kind of the last resort is to cut out the brain, to find out the epicenter, they have intracranial recording measures to just have them in the hospital, see when something comes up, and then the neurosurgeons are able to locate. And while they're in the hospital, they often agree to participate in research with us and work with us, and that's where a lot of our data comes from. So it's a very limited amount of data, and it's from able-bodied people. But it is the kind of only way that it's easily accessible, or like not easily. This is not easily accessible, but that is like accessible in large amounts. Then directly working with like locked-in patients, which is a lot harder. Like those kind of like those users that we would be targeting, to work directly with them is a very long ethical approval. It's very difficult. Like the ethical consent, like informed consent from somebody who's fully locked in is very like it's a whole process, of course. So our research data comes primarily from that source and like working with like epilepsy patients there.
And then like, I mean, I have to ask some questions about the experimental setups, even though you said you are not really involved with that. What is the setup? So I imagine like if you want to have like a mouse movement on the screen for like you want to derive that from the data, so then you have to tell the participant like that they should try to move an object with their mind, or how does like the experiment work? Like
most of the experiments that are being performed in the hospital are not closed loop. So most of the closed loop experiment would mean that you directly see the output, like the feedback is directly generated, right, and you can respond to that feedback again. Most of those are so-called open loop or offline experiments. So they don't directly move the mouse, but like for speech, they are asked to produce a word or an utterance. And for movement, they are like, we track the fingers mostly and sometimes part of the arm, like depending on the setup and what exactly you're using. And then sometimes making gestures like sign language, for example, or just like clenching your fist, opening the fist. Like flexing your wrist is a very common one that has been used because it's a very identifiable signal. So in Utrecht in 2016, they had an actual locked-in patient implanted and with a 4 electrode setup, which was enough to like very reliably have that wrist flexion. So just like kind of like pulling your hand back movement. And that was like a single click. And that was kind of how they interfaced with the tablet. And I think she's using it to that day. And of course, now we have a slightly more complex, and my research in particular is about continuous movement instead of like these discrete classified movements. So like, closing your hand is a very continuous motion. Each single finger is like one continuous motion, or like moving your hand around in space. And decoding that is then a lot more complex than like one very discrete event, of course. So the experiment setups are about that, right? Like how do we just tell the patient, people that the participants that we're working with, like move your fingers one at a time, or wiggle that finger, or like follow a shape on a screen, or can you produce the following words? And then we collect that data and then later with that data set offline in the lab somewhere, we are trying to build models that can then reproduce or decode or use that in some amount.
So you're kind of using actually moving people and how far their motor cortex or their brain is active.
Yeah.
And then try to find a general rule you can use for models to find out, well, is the idea then to implant electrodes to locked in people and see or try to enable them by putting the models produced using moving participants to then enable them to move in a certain way again?
Yeah. So maybe I can use that to like make a bit of a larger, because I think we didn't have like a concise like, summary of how what we're doing or like how this works, or like what the end goal is kind of. The idea is that, like I said earlier, like your brain still produces the signal to move, like your motor cortex is still producing that move the hand or move the fingers signal. It just gets cut off on the way, right? And that's why nothing happens anymore to some extent, or it's not able to follow anymore. But the signal that is still being produced can be used. And that because the motor cortex is next to the visual cortex, maybe like the best understood area that we have of the brain, like we have the most understanding of how it is laid out. And it's fairly decently consistent it's good by brain standards between people. That like, and this is like kind of like where finger activity is usually very well recorded or similar to that. So we can target those specific regions and put like electrode strips over or into those regions and record that activity from there directly. And because we know this is roughly, or like usually people get put in a scanner before, like an fMRI scanner, and they're told to either produce language or like move the fingers depending on what we're targeting. And then you can very directly see, okay, like this is the highest activity region, so this is where we want to put the electrodes in. And then we can use those signals in those paralyzed people to drive those assistive devices, right? So we use our insight that we gained from working with able-bodied people and those models that we trained on that data and fit and make basically like jumpstart a bit the like training. Usually it still requires some amount of training, but jumpstart that and know, okay, this model can work for this. And then we are able to like there's a lot of research in where you can reliably decode these kind of signals from the brain and use them to drive like assistive device technology, so like tablets to communicate, like spellers to or like synthesize language, and or drive a like robotic arm, which like fairly fine-grained control as well nowadays. And I think there have been like some experiments about like full exoskeletons as well. But I think those were like single patient, very highly optimized. And we are trying to look at very generalizable, like how can we make a thing that is as applicable to as many people as we can. Mm-hmm. And then, of course, the idea is to use these signals to get some meaningful output that they can actually engage with the environment, interact, communicate, be part in like the environment again. Yeah.
I'm just... As far as I understand motor cortex, it's not the same as thinking, I want to say X or I want to move my arm, right? So the people do have to be able, or at least they have to be able to imagine moving, or how does that work in paralyzed people?
Sorry. There's a difference between imagined movement and intended movement, right? So I can ask you to sit still and imagine your hand moving. That's imagined movement without your hand actually moving. But then if I tell you to move your hand, in actuality, that's intended movement, right? Because you intend to move your arm, and then your arm actually follows because your body-arm connection, the brain-arm connection is fully functional, or I presume. That motor intention is what we're targeting. So motor imagery is particularly used in EEG. Like in EEG context, we have a lot of motor imagery tasks. But in our context, we very specifically move with actual movement and then the motor intent of those users in the end.
It's super fascinating. I mean, I didn't expect or I wasn't sure if being unable to move your arm, for example, would not like affect your ability to intend the movement somehow. I would think that like after a while since nothing is happening, you don't intend to use your arm anymore, and then the function gets lost, but apparently it doesn't.
Yeah, so this is I'm a bit shaky on that, but I'm pretty sure that we have done research that it's fairly stable over like years after paralysis, like even after years of the event of paralysis, that signal, that like information in the motor cortex is still fairly reliable. So particularly if you are not paralyzed from birth, then I don't know. I don't know about that context. I'm exclusively like looking at people that have been paralyzed sometime in their life. And having built that, like anything between like 2 decades to like 6 decades of movement, right, like kind of stays to some extent for a long time apparently. And so we can kind of build on top of that to use that later.
That's impressive. And then more to the side of computation.
Mm-hmm.
What kinds of methods do you use to analyze the data? Or is there like something, are you still experimenting, or is there something that is crystallized as like a very promising way of dealing with the data?
Mm-hmm. Is that a you as in the field or you as in me directly? Because the field is very broad, and I like work on a very specific part of that, right?
I mean, you seem to be the expert on what you are doing, so that's like the main focus. But if you are like very out there and most of researchers are doing something else, then it would also be interesting what most people are doing.
Yeah, so I mean, generally speaking, you have everything from like support vector machines, so like fairly simple, like closed analytical solutions, models that are able to classify signals, and all the way to like manifold learning has been appearing in like very complex different mathematical models has been appearing in the last couple of years. And I mostly work with artificial neural networks, which also have, of course, as they have influenced anything else where you have data to analyze, they have also been like very successful in a lot of BCI applications. So I work with recurrent and convolutional neural networks to try to analyze that data. It's always working with biological data is always more difficult. Biological data is inherently noisy and comes with a lot of complexity. You have non-stationary signals. So like if you think of a very nice like mechanical signal, it kind of like has a certain 0 point and it kind of oscillates around that 0 point. We don't get that in biological data. You have signals drifting over time and you have to deal with a lot of noise. Like there's so much going on in the brain at all times, right? Like the motor cortex, of course, we mostly record from the motor cortex, but there's so much activity that is spread across the entire brain, right? Like this is this huge interconnected network. So you get a lot of signal, but you're interested in like a tiny bit of it, right? So like the signal to noise ratio in terms of recording is amazing because we're using intracranial data, right? Like our electrodes are so close to the brain as you can get, or like you can only get closer by putting it in the brain, with some of my data also is. So EEG has this like famous low signal to noise ratio, right? Like it bleeds over the entire head. It's like a really complex problem to try to figure out where does a signal come from. We don't need to deal with that. But the neural signal is still so rich, but you're interested in only such a small part. It's like you kind of treat it as noise in a way, right? Like you treat a lot of the activity as noise, but because you're interested in only this small bit of it. And that's like a really big challenge in dealing with that, like really complex data.
And speaking of complexity, is like training an artificial neural network is always like a lot of work, but how challenging is like the application versus the training? So if you train a model, is it then applicable to a lot of humans or just a single human? And then does it then run like on a smartwatch, or does it still need like a lot of computational power?
Again, I'm going to use this question to like make a bit of a larger scope answer here. BCIs as a whole are like very much in mostly research settings. There are very, very few examples.
Can you shortly we talk about what BCI stands for as an
abbreviation? Sorry, did I not say that ever and just use the brain-computer interfaces, or BCIs? Like, so there's these like connections from, we use some kind of neural signal, usually from the brain, and we drive some amount of interaction with that, are mostly still used in lab settings and research settings. So like bridging from this lab setting to taking the device home is quite a challenge. Like there's quite a translational gap, is what it's called, like to translate our findings from the research all the way to people using it autonomously without a researcher by their side at home. And there's like a few examples out there, and like there's more of a push nowadays for that. And like part of the goal of the project that I'm part of is like this, it's called the Intense Consortium. It's like this research consortium that I'm part of. The end goal is to produce something that can be used by somebody actually at home. The idea is to use those findings and translate them. However, using like building a model on this like training data that we have and then putting it to a human doesn't, like to a new person that is not in your data set, it's always going to be requiring some amount of fine-tuning. There's like a huge inter and intra variability of brain signals. So there's a big difference between how your brain signal looks like when you move your hand and how my brain signals look like when I move my hand. And there's also a lot of variety in how your brain signals look today when you move your hand and tomorrow or next week or in a year from now. There's like some amount of similarity, of course, but there's also a lot of difference. And you need to account for that and be able to deal with all of those differences. And neural networks also are very famous for needing a lot of data to like achieve their very high accuracy and very high like measures of success that they have in so many fields. And we don't have a lot of data. One of the things of working with exclusively intracranial, exclusively human data is that we have very little of it. Because it's very few that you get the chance to insert strips into the human brain, and then also you don't have like hundreds of hours with them, right? You have a few hours with each of those participants. Like some of my data sets have less than 20 minutes per participant. Of course, 20 minutes is still a lot of data, considering that we record the sample data at like 2,000 to 20,000 hertz. And anywhere between like 30 and 190 channels. So we have like we still have a couple billion data points, but that makes it kind of more problematic because I have now so many data points and I want very small things out of that data. And then I have very much data per participant, but over very few examples. And then I have many participants again. So like there's a lot of how do we deal with this like small data reality like this? How do we deal with having so little data and still build robust models, basically? It's also why part of my PhD focuses on using both ECOG data and stereoelectrode data. So like ECOG data are these grids of electrodes that lie on the brain's surface and record like directly from the population there. So it's kind of similar to EEG, but you skip the skull. So it's much closer, you get a much like higher spatial resolution. You kind of know it's like if the signal is here, it's very close to the electrode. And that used to be the standard for those epilepsy patients that we're working with when they're in the hospital. And nowadays, a lot of those get depth electrodes, so like longer shafts of electrodes that penetrate the cortex and get like into the deeper cortex tissue as well, which allows them to like better navigate this like dynamic network and like find that better. And then I think also the surgery is less stressful on the patient, but I'm not 100% certain. So we are now generating data with that recording modality, but in the end, our implant is going to use ECOG. Mm-hmm. So it's also now we have the research data that is using stereoelectrode, but all of the devices that we're like looking at to actually bring to end users are using ECOG. So I'm trying to look at, can we use the insights, the signals from the stereoelectrode data, use the ECOG data that we still have and like the limited amount that we still record, and can we use those findings together to like get a bit more data, to get a bit more robust, to get a bit more across the board to build models that then will work better for end users again?
In my brain, just so many questions popped up while you were talking, and I tried to make notes. So
feel free to interrupt me at any time if I go off too far.
Really good. You've just mentioned that you are using two different measure modalities, so the ECOG and the those electrodes which are directly in the cortex. And as far as I understood you, the electrodes directly in the cortex are much more precise to the location compared to the ECOG. And how far are you translating the data from one to the other? Or do you see any patterns since you're also analyzing both data already, where they are similar, where they're really different, and how that could work later on?
Yeah, so they're more specific in the sense of that because they're embedded, they're much more close spatial, right? Like putting an ECOG grid on the hand, like still mixes in with more population, like neural population underneath. The population that they recover is still going to be bigger, but you get like more surface recording like this. They're not very close together, the depth electrodes. So you have very sparse but very spatially localized electrodes, which is a bit different to the ECOG grid, but they have both their advantages and disadvantages. So why we target the motor cortex, because it is so prolific for motor. This is why we get the name from, right? Like it's the motor cortex because it is so involved in everything we do with motor activity when we move. And there is, but there is it's still distributed, right? Like the brain is so connected and everything is kind of everywhere if you go look for it. And some of colleagues in Maastricht have like published some work that they are able to classify movement even if you exclude motor cortex data, right? So even if you only look at the non-motor cortex areas from those depth electrodes, there's still like enough signal that like there's still like enough activity relating to that movement that you're at least able to say, oh, there is movement right now. And in the end, both of them record the same thing, right? Both of them are just time series of data of neural activity. So like if you just plot them next to each other, they look very similar. It's still too early to say where those similarities come in best, and like that's very much what I'm going to work on again when I leave this, basically. But the idea is to see, well, if they're closer to the motor cortex, if they're like closer in space, can we find something? Can we find a model, for example, that is able to like abstract away one level, basically, right? So trying to not get too technical. The idea of autoencoders, if that is not too technical already. So kind of we introduce like a bottleneck and try to use less points of information. So a lower dimensional representation of the data. So we have like these hundreds of channels, like 128 channels or something over this like long period of time. And we try to take like a chunk of that, all of those 128 channels, and then try to put it in less than 128 by time steps dimensions, and just like reduce that to kind of find out the shared information that relates to the motor activity, right? Like both of these electrodes in the end record motor activity. Somewhere in that graph that just wiggles around the line is the signal I'm looking for on both of those modalities. So the idea is that hopefully we can find the way that it is represented in both of these signals, and that it is similar enough that we can combine into one shared representation. So we abstract away from the direct recording into one level of like neural signal representation that is shared between both of them. That makes sense.
Yeah, that makes sense.
And then you are able to abstract like the relevant information from only one measure, or?
So the idea for the next 2 years of my research is basically to try to find something that is robust enough in this low dimensional space to decode motor movement from that lowest dimensional space. So it doesn't matter if I feed the stereo electrode or the ECOG data as a raw input. I can find projections from both of those into my lower dimensional space. So I can take that input no matter where it comes from, and I can put it into this shared space that I've created in a way, like a shared space that my models understand better, basically. And then from that shared space, those models can decode. Then I get the output that I want. Then I can get these continuous movements, mouse pointer movements, or whatever else like we're ending up doing there. So it's a kind of a two-part process, right? Like abstracting away from the actual recording modality, and hopefully finding finding this like bottleneck, this like lower dimensional representation that is still holds all the information I need, but it's now a lot less data to deal with, meaning it's also easier to decode from. But it's robust enough that I can use new patients and new data from like new ECOG recordings or new stereo electrodes and find the data that I need in those as well, and also put them into this lower dimensional space. That's kind of the idea of my PhD project. I can let you know in like 2.5 years if that worked or not.
Regarding the measurements, do your participants usually do the same movements, or do they do different movements and you try to encode different movements?
So I mostly work with existing data, and a lot of that comes from a broad range of different experiments. So there are different movements recorded in different ways. And so there's a bit of an abstraction in both directions going on, where I need to abstract away from the neural signal itself, but also kind of need to be not agnostic, but I need to be slightly removed from the very direct way that the movement was recorded. It's like sometimes it will be one finger at a time, sometimes it will be gestures, and I'm trying to find like all of them are continuous signals again, right? Like if you plot them, they all look very similar again. Like all of them are just a continuous line moving on a graph, basically. And trying to find what drives it is still going to be like one of the bigger challenges, to bridge between of different data sets, right? So trying to bridge between data sets instead of relying on one is like this one big challenge that I'm trying to face, is to use many different data sources to kind of combat that I have too little data to work with, to drive what I'm trying to drive. And I lost my thread a bit. Can you repeat your original question really quick? Because I think you asked about whether they are from the same, like if they all look the same, so all make the same movement.
I was trying to get into the direction and how far you can kind of use and how far you know which movements your participants were doing, and if you know which movements they were doing, if they look similar across patients.
So I do know what movements they were doing. And on some level, right, I have the recordings. I don't have video recordings since we're working in like a hospital. There's like very close, like how much we can like share and use actually. But I do know the experiment setup, and I do have the data, so I can kind of reconstruct from there like what it roughly was looking like. I do not know what other auxiliary movements they did, for example, but of course the experiment, they are asked to remain as still as possible otherwise. And there's a bunch of like other things you need to kind of consider maybe, but like primarily we ask them to move still and then move only what we ask them to move, and that is kind of what we're trying to crystallize out of all of that signal. And that looks decently similar enough between all of the patients, right? Like that's what a lot of the success of BCIs in the past has been built on, is either very long time with one patient or working on these like shared representations that are kind of, we have found a pattern here and this works well for an unseen subject as well still.
And is the overall goal to make or build an algorithm that is able to also do novel movements, or are you trying to build something that is trained with enough data to perform each movement there is or each action there is?
I don't think in the current landscape of what's possible it is feasible to do either of those things. I don't think the map of all the movements that are possible, that's a huge map. The body, there's so many things on the body that move. And trying to like either have like a repository of all of those movements also brings up the question of like how granular you are, and it's too big. That's too many things. So we focus mostly on the arm, hand, finger movements because they are very well represented in the motor cortex. And move your fingers or move your hand is a fairly direct like command that doesn't allow too many different interpretations as well. In the end, the devices and the like end program, or like what is currently being done in the BCI field as a whole as well, when you look at movement, is you still look at like either an individual finger or like hand movement, and translate that into whatever you kind of need it to be. But like in a way, if you think about it, if you use a controller, like a game controller, you map your finger movements directly into a very different output. Right? You can think of that in a very similar manner. Of like, well, yeah, closing your fist, for example, could be moving upwards, like moving downwards, for example, or opening your hand could be the opposite direction, for example, right? And like, if you break it down, it can be every single finger, etc. So that's kind of the basic idea. You have a limited set of movement that is easily understood and controlled. Like wiggle your finger, like flex one of those things. And then you translate that into a useful signal, like moving a cursor around or selecting something on the screen, or maybe even navigate a wheelchair around, right? Like all of those things in the end, just like you can learn how to use a controller, can be learned to map to those things as well. And then you kind of build on the the ability to learn of the end user to learn that mapping as well. Just like when you learn to play games, you needed to learn that at the start as well, or you need to learn to like draw something. You learn a very specific way how to hold pens. Like there's all like, you use all the same movements to drive a new kind of output. Like, so there's still some learning involved. No, I think that was it. But so we're not trying to use all the movement available, or to even attempt to restore all of the movements available right now. There's some work that look at like exoskeletons, etc., which are like, of course, much more. And then it's about like walking and like moving your arms. Those are even further away from being ready for home use than what we're working with.
You've mentioned at the beginning in what you're most fascinated about, and also at some point in the conversation a bit earlier, that not only the motor cortex is involved in motor movements. And I'm still thinking about that you mentioned that even when you're not measuring on the motor cortex, you can still kind of backtrack what kind of movement was happening. Did I get that correct, or did I misunderstand you?
I'm not sure if backtracking would be the correct term to use. So I'm not sure if we're my work colleague in Maastricht will of course be a better person to answer his research questions. But like, if you think about movement, it's like a very long process, right? Like there's planning of movement, there is the execution of movement. Planning might involve like imagining the movement to some extent. It's a like continuous involved feedback role of like your proprioception, like where is it, like did I bump into something. So like there's a lot of continuous movement. Like movement is a very continuous process, right? It's not a like go signal and then it's just done in the brain. And my assumption would be, right, like I can't be sure. My assumption would be that like you pick up on all of those different parts that are part of the rest of the brain. Also because depth electrodes get depth, right? So you're not limited to that, but you also can get some of the lower connection, which is like a lot where the input often comes in first before it gets distributed, right? So you can pick up on those connections as well. And my assumption would be that even if you don't directly have motor cortex signal, which is also the case for all of the data I'm working with, because that's not the most relevant part for the neurosurgeons for the epilepsy patients, you can still get activity from the motor cortex, or like motor activity in different parts of the cortex.
Okay.
I'm wondering right now, like how much you have alluded to it at several occasions, but how much of the thing you are studying depends on what other people wanted to do or measure? Like, in how far do you have control over the data you're getting? You mean that, like, other people recorded it for you and you can control the experiment? And I think like the argument was really convincing, where you would like movement of your hand and also where you would take that as a measurement, and how you can map that to other things. But like that's not something that you ever like consciously had control over in your research, right? So the research is kind of dictated by the data that is available, right?
I mean, I think that's a bit of every data analysis research. It's not. I mean, I talk to the people that record the data, right? Like, they're my supervisors, they're my colleagues. There's like feedback processes going on of what works, what doesn't work, etc. Right? All of these experiments are ongoing as well. So if I have feedback or input that can be heard as well, of course, there. There was the idea of designing a project together, like a whole experiment together across the different institutes as well, because I work with 2 different hospitals, and that turned out to be too complex in the like whole picture of my PhD and the organizations, like to get 2 things that are very aligned and use the same methods and the same like tools, and so there was the idea of having that input, but it was still very similar and was based on top of what those experiments were already and what was already done. Like, there's very few assistive brain-computer interfaces that don't rely on the motor cortex. Some amount of speech reconstruction sometimes moves more towards the temporal lobe, because that's where a lot of the auditory information is being processed, and when you speak, it's a lot where a lot of it is produced. A lot of signal is produced. And there some amount, like in the general research area where Matthesis was part, there's also like cortical implants for vision. So those are implants that are in the visual cortex, and of course. But for what I'm interested in doing in my PhD, I do think that particularly hand movement is one of the most interesting ones. Like the density of nerves and like the very fine-grained movement that you're able to do with your hand has like led to a very strong risk presentation in your brain, kind of. So it makes, at least to me, intuitive sense why I would go for that and try to use that signal to drive the assistive technology.
Mm-hmm.
So we've been talking about quite a lot of technical questions right now, and also in how far data was collected in people with epilepsy, but you're mainly targeting lock-in patients or people at home who are having movement issues to a certain degree. So how does the translation from your research to the product or to the end use look like?
Difficult. So there are like several questions kind of that you need to come into play, right? Like, how do you even approach these kind of target groups? How do you involve them in your research, and how do you make sure your research is relevant to that target group? And I think all of those questions kind of need to be answered before you start making a product. And there is like, what is the best way to fill a need that these users have, right? Like, this is a really high risk procedure it's a very experimental, it's still like in its early stages of development. The like opening your skull is very invasive and like a lot of infectious risks procedure. So it needs to be an equal like high reward to offset that and like solve an issue and solve it better than anything that is otherwise existent for these people. So talking to those people like is kind of the first step in translating from what we do to, or maybe should even be the step before we start doing what we're doing, to identify what is a need that is technologically feasible for us to actually target, and that they need to have fill out, basically, right? That there's something that they can't do anymore, and that we have the ability, or that we see the potential to solve for them. So having interviews with like all of those different stakeholders, which is like the user themselves, of course, but also their caretakers, right? Medical professionals, their like immediate social environment, the people that will be there with them. All of them have slightly different perspectives and like needs, but all of them will need to engage with whatever we are creating, right? Like and that is a lot of the gap, because our research is so focused, often at least, on getting higher accuracy scores, on making that really interesting new thing, right? Like, but what if the wrist rotates 360 degrees? Or like, what if we have a vocabulary of 200 instead of 10 words, right? But maybe that is not the most goal-oriented question to ask if your goal is to help these people in the most impactful way. And having these conversations with these patients and going about and like involving them directly in the research, in this development process, and going on about involving people and like evaluating as you go along, are we on the right track? Is I think like how you approach this step by step. And then of course you need to work with like companies and industry partners to actually build a product that can be used by these people, right? Like going from an implant where the cables are still coming out of the skull to a fully implanted wireless device that can be used at home is like also a very technologically challenging step. So you need to talk with so many different people and like have so many different skill sets together to even combine, like to even approach that goal that you're trying to have. And I think there's a lot of there's work being done. If you look at the citation counts, it's not as exciting to the research community clearly as having a really new funky thing like decoding handwriting from the motor cortex, for example, was something that they did recently. Of course, those things are flashing, get a lot more citation count, but I think it's really important that we think about how do we involve the people that we research for. Yeah, I think that was a good end statement, actually. I've been going on for a bit. We can do many interesting things, right? Like both from an engineering perspective, we can create many new things. I've been at conferences as well where we have like really interesting prosthetic arms, for example. It's like really interesting technology, right? Where like as an engineer, you can ask the question, why should I be limited by the human design, right? Like you can go about having more than, like, why do we only have one thumb? Having a thumb on the other side as well would allow you to grab many more things with like much more dexterity. Or why even limit yourself to an arm, right? Like you can, like there is a prototype, there was a prototype developed that used basically like an octopus-like arm that was like one-dimensional because all you did was kind of like, it was a hydraulic arm, right? And then that allowed you to grab things. But are those things that people want to use is a very different question, right? Like, is it very useful if we can decode handwriting into written words? Is that faster than decoding speech? Is it faster than using like an autocorrect, like prediction text speller? And if it's not, maybe we focus on the other part first. Maybe we focus first on getting something from our labs into their home instead of continuous just like going in our lab and going in our lab and going out and doing the next interesting thing. If our goal and if the goal that we are getting grant money for is to help these people, right? To further to close that gap, to further the trajectory of building a BCI device that can help like these thousands of people that are locked in to gain some autonomy and some quality of life back. Very long ramble. Sorry.
No, I think that's really interesting because we always try to like get the relation the topic has to cognitive science, and I think this is a really good example of two-way streets. So I think like you benefit a lot from like a background in cognitive science because you could like use just a data analyst, if I can say just in front of that, but then they don't have like the background that they need maybe to work with brain data. And on the other side, it also shows from what you said right now that like cognitive science really needs that topic because like that's something where we really can have impact in people's life and don't just sit at home and say, oh look, I wrote this fancy algorithm that does something that I thought would be fun, but like nobody really needs. So I think like that's a really, really interesting topic that cognitive science benefits from, and that benefits from cognitive science somehow.
I would say so, yeah. I mean, I've thrown engineers a bit as an example under the bus, but it's like a problem across like researchers and like medical professionals. Like most people involved kind of sometimes lose it out of sight, because I myself sometimes as well, because it's really exciting if you have a cool new idea. But what you're saying is like very right. I also personally, right, I did study cognitive science here, and I did courses on user experience and perception, and I did courses on human-computer interaction, and I had like this like dipping into all of these kind of different disciplines that now are very useful because they allow me to have insights into like all of these like different facets that are part of this very long process or large process that I'm a very small part of. And I do think that learning from, because cognitive science is like so broad and taps in so many different aspects, but learning from the human aspect of that research is really important. Like, and as you said, it is a bidirectional street where we want people to use our research, right? I think most people are really excited about if their research is being like used somewhere, and so we want people to be excited for our research, and we want our research to be exciting to people, and like that needs this bidirectional input, right? Like we want people to be excited for us, and we need to be excited for these people, and I think that's how we do our best research.
I just really love that statement. I'm just really happy with that statement. If people have listened to that episode, what should they take home? So is there a summary take-home message?
Like I think I'm going to start with a bit of the downer take-home message of like BCIs have seen a lot of uptake in like public media, and they've been around for decades. We've been doing this for a long time. It's not a very new thing, but it's also still very early in its development, right? It's just mature enough that we have now like broader scale human like applications. We have the ability that companies can use that technology, that research, and put it into products, but it's still very much active research and very early in its stages on all of those levels, right? Like from the implant to the like the whole like product package of like how do we implant it and how do we transfer that, to the algorithms that drive it, to the analysis, to the assistive technology. Like there are so many things that need to come together that are all very actively being developed, that I think we kind of need to keep that in mind a bit when we think about BCIs, is that this is still a young field with respect to many other technological developments. But it's a very exciting field. And I think it has a lot of potential for both people to like restore or help them or augment or like give them some amount of quality of life back, and it has a lot of potential for people in their everyday life to I don't want to say like have like impact more, but I think like involving direct brain signal can be really useful in many everyday projects, from like measuring if you're too tired to drive to like replacing lost limbs, right? All of these things are somewhere on that spectrum of potentially on that spectrum of brain-computer interfaces. And I think all of that potential is to be really excited for, but we need to be really careful about the speed at which we try to approach it.
Yeah. So with that being said, thank you so much for coming here. You actually physically came to Osnabrück from... I don't want to say the name because I'm going to pronounce it wrong.
It's Nijmegen.
Nijmegen?
Yeah.
Okay.
I mean, from one not fully correct pronunciation like,
to another even
another not
slightly
fully correct
worse.
pronunciation. People know what is meant. Nijmegen is a city in the Netherlands. So it's fine.
But thank you so much for making it here physically to talk to us and having this really interesting conversation about brain-computer interfaces.
Yes, thank you so much for having me. It's good to be back here, and it was a pleasure.
When you enjoy listening to us, the best way to support us is by following us on your chosen podcast app. This could either be Spotify, Google Podcasts, Apple Podcasts, Amazon Music, or the website of the Cognitive Science Student Journal. Another good way to support us is by following our Instagram account, which is called kaleidoscience_pod. On our Instagram account, you will also get regular information on the next episode. Thanks a lot for supporting us. This was Kaleidoscience, hosted by Elisa Palmer and Sönke Löw. Produced by Alina Ohnesorge, Elisa Palmer, Sönke Löw and Sophie Kühne. Produced in collaboration with the Cognitive Science Student Journal. The music was produced by Jan-Luca Schröder. The logo was designed by Annika Richter. Thank you for listening and joining us on our journey through conversations on cognitive science.